Hello, this will be a demonstration of Proposition 1 from Book 7 of Euclid's Elements, which says that two unequal numbers being set out, the less being continually subtracted from the greater, and if the remaining number never measures the number before it until a unit is left, the two numbers shall be prime to one another. The modern language for prime to one another is a coprime, which makes a decent amount of sense. So if I ever say coprime instead of prime to one another, understand them to mean the same thing. Okay. So we're going to have two unequal numbers, number AB and number CD, and we're just going to say that, the number CD is less than the number AB. And we're going to continually subtract the less from the greater such that the remainder never measures the number before it until a unit remains. And if this be so, then the numbers AB and CD shall be coprime. They will be prime to each other. For if this is not the case, that AB is prime to CD, then some number will measure the both of them. I mean, that's what it means to be not coprime, is that you have a common measure. And so, if the number AB is not prime to the number CD, then some number will measure them. We'll call this number E. And number E will be such that it measures both the numbers AB and CD. First, we're going to have CD measuring AB, and this is going to give us the number BF, and the remainder shall be the number FA. And furthermore, we'll have the number AF measure CD to the number DG remaining, or with the remainder being the number GC. And finally, we're going to have the number GC measuring the number FA to the number FH, leaving the unit HA as a remainder. We know that the unit H, that some unit is going to come up eventually in this series, so we're just going to say it comes up here, and it's going to be the unit AH. Now, because the number E measures the number CD, and the number CD measures the number BF, we know that E measures CD by the first step, and that CD measures BF by the second step. We can thus say by a property of numbers that E shall measure BF. This would be like saying that 2 measures 4, 4 measures 8, so 2 measures 8. It's very obvious, right? So the number E also measures the number BF. But in the first step, we had established that the number E also measures the number AB, which means that it measures both the numbers AB and BF, which means it'll measure their difference, which is the number AF. So the number E measures the number AF. This would be like saying that, let me think, 3 measures both 18 and 6, which means that 3 measures their difference, which is 12. And this is obviously the case, right? So the number E measures the number AF. Now similarly, because the number AF measures the number DG, we have made it such in the second step, we can also say that the number E measures the number DG, but the number E, we made it such that it measures DC, so it measures both the number DC and the number DG, which means it measures their difference, so that the number E measures the number CG. Now, the number CG measures the number FH, which means that the number E also measures the number FH, but we had established in the fourth step that the number E measures the number AF. So the number E measures both the number AF and the number FH, which means it'll measure their difference. And their difference is the unit AH, so that the number E can be said to measure the unit AH. But this is manifestly impossible. The unit is measured by no number. That is by definition. And so we have it, the case, that the number E both measures the unit AH and also that it does not measure the unit AH. This is manifestly a contradiction. So we can say that our premise that the number E measures both the numbers AB and CD is false, and we can say this about any number that we might say measures both the numbers AB and CD. We'll reach the same absurdity that this number will measure the unit, and so we can say that no number measures AB and CD in common, so that the numbers a, b, and c, d are prime to each other. Now, this is exactly what we set out to prove, which means we are done with the proposition, therefore, etc., q, e, d. Now, this is not the most clear without an example, so I'm going to go through an example right now. Let's say we have two numbers, 25 and 108. And this process of continual subtraction, it actually has a technical name. You're either going to hear it called the Euclidean algorithm, or the significantly more complex term, antinaresis, which is a fun word to say. But it just refers to this process of continual subtraction. What this is going to look like is that we're going to take the lesser of the two numbers and subtract it from the greater until we get a number that cannot be subtracted. So in this case, we have a 108. We're going to subtract 25 from it. We're going to be left with 83. 83, we can subtract 25 from that again, so we're going to do it again. And this is going to leave us with 58. 58 is still greater than 25, so we can subtract it again. So we're going to be left with 33. Now 33 is again greater than 25, so we can do it again. So that we're left with 8. Now 8 is not greater than 25. It is in fact less than 25. So we start the process over again. This time making 25 the greater and 8 the lesser. So now we have 25 minus 8 as opposed to 108 minus 25. Now, let's subtract this. So 25 minus 8 gets us 17. 17 is yet still greater than 8, so we can do it again and subtract 8 from it. 17 minus 8 is 9. 9 is yet still greater than 8, so we can do it again. And look at that, we are left with a unit, which is just 1, which for Euclid is not a number. Okay, not just for Euclid. 1 just is not a number. But the point is that this process of continual subtraction brings us to the unit. It brings us to 1, which means that we can say that 25 and 108 are co-prime. That is, they don't share any factors. And this is the case. Euclid doesn't get to showing the fundamental theorem of arithmetic that all numbers can be represented as a unique product of prime numbers, obviously excluding 1, because it's not even a number to begin with. 25 is just 5 squared, so its factors are just 5 and 5. 108, its prime factorization is a fair bit more complicated. It's going to be 3 squared times 3 times 2 squared, which is 3 cubed times 2 squared. Like that. That's actually a fairly nice factorization. And so we see that they don't share any factors. 25 is only made up of 5s, and 108 is only made up of 2s and 3s. So, yeah, they are co-prime to each other. And this proposition 7.1 gets us to that, not by using prime factorization, but by using this process of continual subtraction called antinaresis. This is very useful, especially if you want to do some coding. This is quite easy to make. And that's fun. You can do that if you have some coding knowledge. But yeah, this is a very, very important proposition. It's the first proposition for number theory in Euclid's Elements, so it obviously holds a preeminent place for that reason, but it's also just very useful to be able to show that two numbers are co-prime to each other by doing this continual process of subtraction until 1 is reached. Now, that's all I have to say about proposition 7.1, which means I'll end the video here and move on to 7.2.